Big drum roll. We're live. It's happening. We're back. Another live session with SAI, and Caleb's here. Caleb has done a lot of work on SAI, and he's going to be able to once again help me figure out what I'm doing, which is pretty exciting. It's always nice to have that. I'm just going to jump right in here because we were talking about some stuff about SAI, about the code, and about the performance side of things. So what did I do? Broke my thing. Hold on. There we go. Let's see if I got this right. I'm currently inserting a bunch of data. I have been going on and off. So this is doing like 20,000 or 25,000 a second. I'm just going to cancel that and get rid of the populate phase here, and I'm going to have it switch over to doing reads. And I don't know. I have a feeling 10,000 a second might be asking it a lot. So I'm just going to slow it down. And then one thing I did, Caleb, after our talk last time, I added support. Actually, here, let me just take this off. So basically, just in case you didn't catch the stream last time, I had a cluster set up, and I was really kind of going nuts on it. Like I definitely managed to break a bunch of stuff. But the good thing is that in the process of breaking stuff, we got valuable information. So that makes me happy. Okay, now, so I'm just going to run, let's check this out. The last time you asked me if there was a limit. So the workload that I'm running this time is a little bit different. It's not a, it's still, this one was not a global one. This one's, and I changed the, if I do that, whoops. Fields, come on, that should work. What am I doing here? How do I not know how to use my own tool? Just a sec. Anyway, it's okay. I'll just kick this off. The thing that I was doing last time was the rows were kind of small, and in this instance, I've recreated this, but I have more rows in here. So we can restrict things by partition and do a SAI partition search. So that's what it's going to do by default. And I also changed the default field that my SAI test uses. So originally it was like randomly generated characters, but it was doing so many of them that, sorry, no, it wasn't randomly generated characters. It was sections out of a book, but the values were random enough, and it was high enough in cardinality that there was just no what's it called? Oh, okay. Wait, do we have no audio? Can you hear me okay?
I can. I'm not on YouTube.
Oh, okay. Well, someone just told me that we lost the audio. Well, hopefully not. Anyway, what was I saying? Stuff. I did stuff.
I think we were talking about the fact that the text we were indexing was like a ton of unique values, and there wasn't much compression going on in the terms index.
Right. So now, now what we have, it's a little bit better. So there's the SAI default workload is using an index of last names. There are 88,000 unique values that I have for this data set. So now that I've done several million Let's see, how many do we have in here? No, don't populate. Don't populate. We don't need a billion rows populated right now. We're not waiting for that. I don't have time. Okay, so this is our wider partitions, 100,000 of them. Running this workload for up to a day, 10,000 queries per second. Go. And then, like I said, there's 80-something thousand unique values. So as this is going, I'm going to be messing around on here. Oh, and I also added, Caleb, because last time you asked me for if it could do a limit. I added support for a limit into this workload. So if you're curious to see what happens at limit, we can, because I think a lot of workloads are going to be like, give me 10 things or something. One thing that's kind of interesting is
this kind of puts a lower, like an upper bound on the amount of latency that's coming from like the local reads, like the post filtering reads and whatnot.
Yeah. So one test. So there's like 3 ways to do this that are kind of interesting. It's one, like, give me, all the records in a partition that match this value. That's fine. There's also the global one. The global one I think is pretty valuable. I think a lot of people are under the impression that SAI is going to be like a magic Elasticsearch replacement. We were just talking about how that's not the intention here. This is not, literally V1 is not supposed to be you're not supposed to be ripping out Elasticsearch. We don't have, as we talked last time, we don't have tokenization. So it's like, you can't do full text search here. The token is whatever you've put in for the field. So there is no, it literally is just a replacement for secondary indexes for a limited use case of within the partition search. And I feel comfortable saying that, that it will work for that use case, but not so much for global ones. And I think, yeah. But one interesting thing, if we do decide to test global, is EasyCastRS has the option to paginate through all its results. So normally you just get the first page of results, but if we had 1 million results come back for a given search, then you'll only get the first page of them. And so that doesn't really, it might not reflect like how a real world application is going to behave. So now it's like you can do -- paginate and it'll go through it, which to me is, I think that there's actually a lot of value in doing that. So that's just something we can probably mess around with at some point. Good. All right, so let's take a look. Oh, and this is also set to do a lot of writes. So I'm going to switch this up. We're going to do a lot of reads. This is going to be like, I'm thinking, since I already loaded a decent chunk of data in here, let's go with 80% reads. And then let's just take a look at what's happening on the Cassandra side of things. All right. All right, so what did I configure this with? Oops. I think it was 10,000 operations, something like that. So this is doing its warm-up phase right now. The warm-up stuff is pretty cool. I added this a couple months ago. So now you can, now by default, whatever you put your rate limit at, because the original TLP stress didn't have a scheduler. So now there actually is a scheduler built in, which helps identify certain types of issues. It also can result in like putting more pressure on the cluster if you're not careful. And anyway, I forgot where I was going with that, but oh, the rate limiter, the warm-up phase. That's what it is. Now we actually have a decent warm-up system. So I'm just going to go ahead and grab a flame graph so we can see what's going on while we're doing these reads. And then I'm going to grab an allocation flame graph as well. And then we'll just take a look at open those up and take a look at those and see where our CPU time is spent. I've also been working on off CPU profiling. So I don't think that, well, I'm going to check to see what the numbers are when we come back from here. But if we're not seeing a lot of time spent in system time, then, or if we are seeing a lot of time spent, then I'll go ahead and do an off CPU flame graph. We can figure out where that time is being spent. I have a feeling that we're going to see some stuff with futexes and spinning from our SEP worker. So, okay, so as we're looking at this is interesting that our write latency is so high compared to our read latency. We're doing significantly less. Let's just jump on here. In case you're hearing a sound, that's my dog in the background. She's not being abused. She just gets really upset when there's a dog on the other side of the fence. So last time when we looked at this, oh, okay, cool. I had done 34 million inserts. Last time when we looked at this was super backed up. Whoa, latency dropped down. Wonder what was going on there. All right, I'm gonna grab this flame graph, take a look. What do you think we're gonna see?
I don't know. Well, so we got what would be 80-20 reads and writes.
Yeah.
How big do you think the partitions actually are at this point?
Good question. Let's do.
What I'm still hoping to see is, at least if we isolate the read part of this single partition read command for the post filtering reads.
So have any performance changes gone in here since the last time we looked at this?
Not since the first stream, no.
Okay, cool.
Although when we got that one last time, I think that was a global search and not a partition or restricted search.
Yep.
So that one would have to issue multiple single partition read commands either way.
Okay. Will it would it help if we ran like pre-populated something where there was like, you know, like a smaller range?
So it depends on the limit. Like it depends on how many matches we end up with. So if the limit was like 10 and we're getting like about that many matches at least, it's all good.
Okay. Well, what I'm wondering is if we were to do like only have like 100 partitions, but put like 100,000 records in per partition. But that might take. I mean, that might take too long to populate. 10 partitions, 100,000 each. That's easily doable. In fact, what I will do is I will start up a second one. Let's go.
There's another question here of like, we have our like P99s in the 2s here. When it spikes, why is it doing that?
Oh, there's a question?
Oh no, I guess that's another one of my questions.
Right. Oh, well, yeah. I mean, almost certainly GC.
Yeah.
We could definitely look at that, but we can also source. So let's just go ahead and fire up the second stress test. So easy cat stress. So we're going to run the SAI test, but this one we're only going to do 10 partitions. We're going to do workload.rows equals 100,000. So that's
Just
We'll
some
do,
big old partitions.
yeah, why not? Like, who cares? These will be 90% reads once it's done. And I can't think of anything. Oh, D. Let's just run it for an hour. Okay, so
it looks like the other one has pretty much stabilized up to the 10K. Latencies are stable. So yeah, that one would be a good target for probably some CPU profiling, I'm guessing.
yeah. So let's just add this in. One thing that's pretty fun is like, I think there's kind of a desire to have like a much more flexible configuration built into this to be able to execute like multiple workloads at once. And I kind of take the perspective that that's what processes are for. Like, I just don't care.
Yeah.
So yeah, it definitely makes things a lot easier to just let the operating system do it. Right. So this is going, and this, by the way, is doing the 80,000 the queries against the text field. So if we want to do it against the integer field, we can actually specify custom range. So if we wanted to say, like, let's put 1 million, whatever, 10 million records in, and then but also like restrict the range of the value of the integer value to like only 100, then you can deal with like super low cardinality searches. So those will be kind of an interesting thing as well, because I think there's going to be a lot of use cases. And I'm not endorsing this, by the way. I think that this is a terrible use case for SAI. But you can tell me if I'm wrong. Putting it on a field like status, where you've got like in progress, done, and like pending. Like there's a lot, like the temporal project.
Yeah,
for example,
what I think you're going to have, yeah, like what I think you're going to have is it's not so much an issue like with the old secondary indexes, the legacy secondary indexes. You had this kind of best practices thing, which was, yeah, if your cardinality is like, in the most pathological case, like a Boolean, you're going to be in bad shape because that thing is implemented as a table, and it meant you just had these two enormous localized partitions, right? And those all, had, those primary keys, the clusterings were, pointing back to the source data, and those clusterings did not compress at all. The thing that's a little bit better with SAI is if you do that, the postings are at least very compact.
Yeah.
Like you might store like a bit per posting or something like that, right? Because those things are just numerics, and they're gonna compress really, really nicely. Like say if you have a Boolean. But still, the point is, like, regardless of how well those look on disk, and they'll look fine. Like it'll be a super small terms dictionary and super compressed postings. But the point is that even if you do that, if you're querying the non-selective end of that data, like let's say you had a Boolean, you indexed a Boolean for some reason, and 99.9% of your data was false and the rest was true. If you're querying the false side, it's pointless. You should just post filter, because it's not. Now, if you queried the true side, like if you queried the side that's 0.1% of the data, that's extremely selective, and that actually could be useful. But it boils down to your query patterns.
Yeah. I'm expecting the performance would be worse, since at least right now, because of the way that it does point lookups, like it becomes an ON operation with fetching rows individually rather than like through a scan.
I mean, it won't be. Yeah. So the performance of that query is still going to be like your latency will still be dominated by how long it takes to do those individual row lookups. Something that we actually have room to optimize still, but yeah.
So this one right here that I just started, I think because I didn't specify a rate, it'll just work its way up to 5,000 queries a second. So I'm just going to take a quick look here at the. So we've got two concurrent stress workloads, and the writes are looking pretty good now. It seemed to be kind of like an anomaly there, where it was a several hundred millisecond pause. But the overall CPU usage is not looking bad at all. I think we could definitely put a little bit more through this, but let's just take a look at the flame graph.
That's two workloads on the same node or same cluster.
That what?
That's two workloads on the same cluster.
Yeah, it's actually two. It's against the same table. So some of the rows in this table are going to be really hot, and so the one thing I could actually do here to make it so that I don't need to run two workloads like this is to be able to add in like change the way that, like, when it populates data in the beginning, it does so sequentially. I could have it do like more of like a Gaussian distribution, or I think like Zipfin or something like that. I think is another one where it's going to weight things more on one side. So those will actually be kind of interesting to put in, because then we can have more like topological use cases and just make it like kind of standard built into the tool. And I even have a thing for that. All right, I'm just going to open up. Let's see. So while this is running, I'm also going to have it do an allocation flame graph. So then I can switch to that when it loads up. All right, let's take a look. All right.
Allocation or CPU here?
This is CPU. So it looks like 13% of our time we're in some GC related stuff, which is kind of interesting. But that's from, that could be, that doesn't necessarily mean it's blocking. It just means it's doing a lot of work, potentially concurrently. And then like this concurrent working task. So I'm not intimately familiar with all this full stack trace, so I would need to look, but I'm not sure which one of these are blocking. But I'm pretty sure it's not the one that says concurrent. We've got a lot of oops. Just going to start up MP-stat so I can look at it. Okay. What are we looking at here? We've got a decent amount of time spent in Park. We can ignore that. Those are threads that aren't doing anything.
Yep.
What do we have here? You know, I should really generate an off CPU or wall clock CPU or a wall clock profile while we're doing this as well. I'm currently seeing about 5% of time. So it's 20, according to MP-stat, I got about 21% of my time. Hey, Millie, calm down, buddy. I got 21% of my time in user and about 5% in system time, almost no time spent in IO wait. So I have a feeling that the system time is actually being spent in the in here. That makes the most sense given the size of this block. So it's, unfortunately, this is one thing I've noticed a few times is the where these threads are just on like this parking sep worker. We end up seeing a lot of time CPU time relatively. Kind of want to get rid of that. All right, let's open up the allocation flame graph. I'm assuming you want this.
Yep. Definitely want both.
Yep. Anything in here we should be zooming into?
All right, so it looks like we got like 3 blocks here.
Yep. The big one here, 20% is spent in unfiltered partition iterator. And
yeah,
then over
that's
here
all.
we have the.
Okay, yeah, there we go. Okay, so keep going up on that one. Let's see, that's okay. Yeah,
I can
the actual. Okay, yeah, so this is the actual. This is actually searching the index. So you see literal index segment searcher search there. That's actually hitting the terms index and materializing an iterator of primary keys. So that, and if you go, yeah, that's spread out in a bunch of different places. But that chunk right there, so in the middle there we have wide primary key map. What that thing is doing right there is it's taking the postings, which are row ID, they're just integers. There's row IDs, and they correspond to a particular SS table, and it's looking up the primary keys. So this is a, you know, and yeah, a lot of that is actually in. Yeah, that's validation on the. Anyway, so yeah, the key lookup thing right there in the middle, that's taking row IDs and looking up primary keys. So this is again about what we would expect.
Okay.
The primary keys are still in their own data structure, even though obviously the primary key you could materialize from other parts of the storage engine. Like the primary key exists in the data files, for instance. In the BTI format, it actually doesn't, because we don't actually strictly index the entire primary key. In the big format, in the pre-try format, you actually can get the primary key from the index file, from the I file. So the thing with trying to read, like one of the reasons why we have that as a separate structure is if you want to go and like materialize all that from the data file, you're going to read chunks that have nothing to do with that primary key. Like it's not going to be a dense block read of primary key lookup data that you need to make the index fast.
Yeah.
So anyway.
Okay.
Now, if we zoom back out to the read command create response bit, I think. The chunk on the right, I'm not sure what that is yet, but the one on the left, I'm pretty sure is yeah, like in here. All right. Get next. Cool. Okay. Yeah. So this part right here is skipping. So actually interesting that we're skipping here. So these queries again, we're not paging, right? So we're not paging. And what this is doing is so you'll see here the key range iterator skip to. So when you go to the terms dictionary and you look up your term, you're going to get back a postings list, and that postings list is again it's a bunch of row IDs, and so and they don't have any awareness of partitions. So that's like for a single SS table, right, which may have many partitions. So what this is doing is in all the postings lists you're getting back from all the indexed SS tables, from all the like SS table adjacent SAI indexes, this is just skipping to the partition in the postings list that we want to start reading from. So that's what's going on here. And again, like this, we're all in the index still. So I think now if we zoom back out to that third block here.
Over here? First one?
Yeah. I think that's one we already looked at. And I'm trying to figure out here where. Okay, here we go. Oh no, that's in data resolver. Okay, all right. So this is interesting. So the first thing that is interesting to me here is that really nowhere in this profile is it super prominent. The local reads, if that makes sense. So the local post filtering reads on the individual nodes, they don't seem to be showing up as like a huge sink here. This guy here, so in data resolver, if you go to the kind of the chunk in the middle here, the one that starts in like compute next or in storage proxy, either way. Yeah, here we go. Okay, so this is in data resolver when we're trying to. So this is at the coordinator right here. This is at the coordinator. And we're sitting here waiting for the responses from are the reads quorum here?
No, these are actually by default they're 1. Do you want them at quorum?
Are they 1?
Now I'm doubting myself. Now I'm like,
I want to say that they cannot be 1 because in here, when you have in the data resolver like pre-count, filter, blah blah blah, that I don't think that should be happening. Like I don't think we. Oh yeah, okay. See this thing where it says data resolver resolve with replica filtering protection?
Yeah,
that should not be happening if this is a CL1 read.
Only one way to find out.
But
let's look at it.
Assuming this is a quorum read, what's happening here is there is a mechanism in the range read apparatus called replica filtering protection. And what it does is when you have index queries or filtering queries, it handles situations where locally, like on replicas, an index may not have a match for a particular query, and it will be silent. So we have this notion of a silent replica, and this can happen for individual columns, for rows, and when you have a situation where you have a replica that says, "I have a match for your index query or for your filtering query," and it sends you a match, you have another node that might be actually more up to date, potentially. It says, "I don't have a match." It's going to send you back nothing. When the coordinator sees the one replica, the first replica has a result, and the second replica just gives you nothing, it has no idea. It doesn't know if that means that the new replica, the other replica, is more up to date and there really isn't any result, or it just has no data. Like you have no idea what's going on there. So what you essentially have to do is you have to complete the read. You have to complete the result by going and just asking for that row or that partition from the replica that's quiet, the silent replica, and then you can get that and then resolve the data, like continue along with the read. So there were a bunch of things that had to be actually fixed in this mechanism. In a recent 5.0 blocker ticket, Cassandra 19018. But yeah, this is when you look at the distributed query path for SAI and for filtering in any index in our current indexing, that uses our current index framework. This is one of the biggest chunks of overhead at the coordinator, is having to do this. It's this mechanism to make sure that index reads can actually meet the consistency guarantees that can actually do that correctly.
Gotcha.
If you were to have something like, a real consensus protocol, like say you had a chord, right? Say a chord was done right now, and I wave my magic wand.
Yeah.
All of this will go away. completely. So
right.
if you look at this profile, this is actually a very good indicator of why when a chord is ready, queries like this, like index queries, will probably be faster while also providing better consistency guarantees. Because like on a quorum query, they won't, number one, they'll only hit one node. They won't actually have to hit multiple nodes and come back to the coordinator and like resolve things like what we're doing here, which could like be multiple passes, you know, to complete reads and replica filtering protection, all that. You know, they agree on the timestamp and there'll be overhead for the protocol, obviously. But once you're past that, it's a single node read, always. Anyway.
All right.
It's fun to see this, actually.
One thing I'm not sure about. So I've been trying to figure out like how can I verify your the issue with the consistency level, and I was curious if there was a virtual table that exposed that information, and I don't think there is. And like there's a metric internally that exposes.
There should be something in client metrics that gives you like indication of what like how many reads at different consistency levels.
Yeah, there are, but what I don't remember.
I mean, just like a priori resolve with read repair, for instance, that should never get hit if like it's a CL1.
So by default, this uses consistency 1. And if you want, I can even explicitly set it, but I am just looking at, I just double checked the source code of EasyCastLab, and it sets the default consistency level to local 1. So I'm not sure. Anyway, I have a another visual that I'm going to bring up. This is the off CPU flame graph. So this is where all of our time is spent from a system perspective. When we have like sys overhead, looking at MP stat. So as expected, unsafe park. This gets called like a lot. And then within the dispatcher as well. So this is all, yeah. So that's where that time is. Reverse flame graph, CPU flame graph. Wasn't sure if this would be helpful for us. It's a little hard to read because there's a lot of stuff at the top, but this kills me.
That's scary. What's the overall CPU usage there is like 20-30%? A lot of these things parking and going to sleep without nothing to do.
Yeah, 30%. I can push this harder, or if we want, we can also get a. I'm gonna get the same type of flame graph, but reverse for allocations, because I just want to see what data structures we're doing the most. I'm fully expecting it to be like byte arrays, lots of them. But you know, occasionally it gets surprised.
Yeah.
So this still has its the two workloads running. It's doing about 12,000 reads a second with another 2,500 writes a second. I'm thinking I'm just going to throw another workload at this thing. maybe do a smaller number of global queries. So let me just switch my screen over. It's this one. Oops. So
I'm probably gonna have to drop soonish here.
Yeah. All right.
And honestly, I might be wrong on the. I might be wrong on the resolver being hit for CL1, but anyway. All right. Yeah, I'm gonna drop, but
Okay.
definitely, yeah, for these partition restricted cases, any and all flame graphs we have for allocations or for CPU, especially when we have like a pretty stable latency profile, like has been the case for most of this. Those are all good.
Yeah, I've got a whole bunch here for you. So
what's nice about this in some ways is like, I mean, we're doing writes here. I mean, we're writing to mem tables, we're flushing, like there's it is a mixed workload.
Yep.
And yeah, I mean, at some point, like most of the index is in memory, I'm sure. But you know, being stable for this is better than not being stable for this.
Yeah.
Oh.
So if I do this, I think that this will do what I want. So this is going to basically there's 1,000 unique values. You know what? Let's just make it 100. We'll just do it 100 values. Yeah, I'll just keep going here. I know that you're going to want to see all this. I'll keep these workloads as well, so that you know kind of what I was up to, and cool. I'll get you all this data when I'm done.
Nice.
Yeah. All right. Yeah, man. Thanks for joining, bud. Appreciate it.
Yeah, it's always fun.
Yeah.
Especially when nothing is super exploding while we're talking.
Hey, man, as soon as you leave, I'm breaking it.
Go for it.
All right. See you, man.
Catch you later.
Bye. Okay. Now we're going to go into my cool view where I'm very large in the corner here. Let's see. Let's see. Let's fix this. This doesn't look right. Come over here. All right. Okay, so what I'm doing here is I'm gonna run a third workload against this. So these two are still going to keep running up here. And this one says easy cat stress, run SAI. We're doing 1 million partitions. This is restricting this dash field value. You know what? This is actually wrong. I need to fix this. This should say field.sai.value. So what this does right here is this field.sai.value in equals random 0 to 100. What this does is it basically is just saying like that's how many random, that's the generator for that field. So the cool thing is that like because I'm mixing it between data sets, some partitions are going to get larger, some are going to get, you know, the rest of the data. But this is going to be a global query. So let's see if I manage to do it right. And then actually, I'm also going to stop this. So I'm also going to set workload that limit equals 1,000. So I'm only going to get 1,000 things out of here. See how it goes. And you can see here where it says preparing select workload limit is 1,000, global is true. So we should get some more data. As basically what I'm going to keep doing is I'm going to keep putting more and more load in this cluster, and I may even start adding in some like arbitrary other workloads just to see what happens as things start interacting, because it's nice to know like what happens if you have a time series workload at the same time as this or something like that. There's always cases where things interact. Okay, so this is going, so while this is running, let's just take a look back on here. Okay, so now we're in the 40s to 50s on CPU usage. And then let's just make sure we sort by that as well. So per disk memtable something, memtable flush writer. So I wonder what that was. So there's a thread called per disk memtable, and then it got cut off. Probably writer, I'm guessing. It's interesting that shows up. So this is one thing that's really nice about this utility, HTOP, is you can, if you use hit F2, you can go into the setup mode here, and then you can add a bunch of different meters in here. But the thing that I really like is to go into column and to go into display options and and enable tree view, and then also enable show custom thread names. Makes it really easy to spot stuff. And then if you sort by CPU and you search by like Java, it'll be sorted under the process by the name of the thread. So here it's like native transport, mutation, whatever, compaction. So it's nice to get a high level of what actually is taking your CPU time. The one thing that's a little unfortunate is the SEP worker makes it harder for observability as well, because what the SEP worker is it's a pool of threads, and the idea has some technical merit to it. It's not a it's not like it's a bad design or anything, but it does make certain things harder. So from the standpoint of like, you know, having a general thread pool, if you want to name your threads, which we do, it means that you have to set the name of the thread for every operation that you're doing, because it might be doing this one thread might be doing a read and then a write and then a read. So every time it has to rename the threads. So there's actually a little bit of CPU overhead associated with renaming the threads. If we start pushing this harder with probably not a SAI workload, but something that's not as CPU intensive, we would actually start to see the thread renaming show up in our flame graph. So it actually does get a meaningful amount of time. You know, not the biggest thing in the world. There's other areas that we should do some optimizations. Let's just do this. Let's just get a wall clock profile when this thing is running as well. All right. Yeah, so this read latency, so this is much higher over here. And that's because it has to hit, that's because it's doing the global query. So the global queries, the more SS tables you have, the longer they're going to take. There's no magic that can fix that. Maybe there is. Maybe there is, and I just don't know it. I don't know. Maybe there's some great magic out there. I'm just gonna grab the output of this flame graph as soon as this comes in. So I'll just switch my other screen here. Okay, and then let's open this guy up. Oh, this is my wall clock profile. I need to exclude this. This doesn't help. Whoa, my reverse profile. All right, I'm just going to run this again. So here, actually, I'll share this because this is kind of interesting. Maybe if you care about generating flame graphs. All right, so we're back here. So reads here, look at this. Reads are only at 36 a second. This is doing mostly writes. So this is basically doing about 4,000 writes a second. And what's interesting about these latency numbers is that these are like picking up. So this is 500, 800, 900. I'm just going to guess that if I do node full TP stats, maybe we'll start to see some stuff queuing up. No, we're not. Oh, yep, there. Okay. Well, we're behind on compactions. So sometimes when these numbers go up, it can be an indication that there is queuing happening internally. Because the way that this runs and the way that a lot of stress tools run is there's a thread that's a scheduler, and it puts stuff in a queue, and then the actual process that's executing the queries pulls things off of that queue. The reason why you want to do that is because of something called coordinated omission. This was something that the first version of TLP stress was actually susceptible to. I was talking about it a little bit earlier. But essentially, if you allow the server to dictate the rate in which requests are sent to the server, then if requests slow down, then if you tell it 5,000 requests a second and it's not actually generating 5,000 things a second, then you can end up in a spot where you get kind of this false sense of security about your application. Let's just run this for 2 hours. So what I'm going to do now, I'm going to run a wall clock profile. Wall clock profile is a lot different than the CPU profile. So the problem with the wall clock profile is that if you have threads that are sleeping, it's still timing them. So it's not particularly helpful if you have this thread pool mechanism where threads are chilling. We don't need to report their time. It's not helpful. So what I'm going to do, and off because it's too much of a pain for me to switch around, I'm just going to just tell you what I'm doing here. The async profiler is the README in the async profiler is really, really nice. So, I always recommend people use the async profiler. To me, it's I think it's the best tool. And there's some recommendations in here about wall clock profiling, how you probably don't want to time threads that are sleeping. So for example, when I run this, I'm going to run this again, but I'm doing, so I do -E for wall clock time. and then at -x and unsafe park. So this is essentially just going to block out any threads that are sitting there in that async park time, which is kind of a lot. And then I'm going to output it to my artifacts directory. Okay, and I call it wall no park threads. Let's see if this works. I probably did something wrong. Oops. Of course I did. Oh. Standard process. All right. So once this is done, I'll pull this down. Easy Cast Lab makes it pretty easy. So anything that's output into Mount Cassandra artifacts, when I'm done with this, I'll go down to, let's open up another one. So basically, there's a command called CDL, just Cassandra download. And when this is done, I'll run this command, and it's going to download all the artifacts that are on the remote instances down to my local instance. And just a little bit of background. So this tool, back when I started it at the last pickle, it was pretty cool. Like I actually really, I still think it's a really cool tool, the original version of it. But there were some things about it I didn't like. It was, it took a long time to bring up clusters. Like to me, 15 minutes is just too long. And I wanted it to be closer to like a minute. And that's what this does. This lets me bring up a cluster of any version in a minute. And it also automates kind of like a lot of the little workflow things that I like being able to quickly take a flame graph. Like these right here, like I'll probably end up adding in shortcuts for all these things so that I can, you know, get nice flame graphs for the different types of things that I do frequently. Let's do that here. And that's my dog. You can hear her. She's a lot of fun. Let's open this up. All right. Wall clock. Kind of not that helpful here. So once we zoom in, so I probably run this. Running this again, I'd probably actually run this and just say like, maybe a couple different versions of this, like aliases to get like sep worker, you know, like limit the stacks to things that are inside the sep worker, or compaction, or really anything, like breaking it out so you can monitor individual things and figure out what's happening in the CPU time. I think that would be pretty cool. But this is what's going on from the CPU. So from a wall clock perspective, it's a bit. What's this? Okay. What's this? So anytime I see like no, I am gonna generate that. I'm gonna do it again. So remember I said, oops. There we are. So I said I was going to do it just by looking at the sep worker. So if I look here, it says sep worker.run. So let's just go ahead and let's try that. By only including the sep worker, I should be able to tell a little bit more. I'm actually going to save this. This is handy. You can't see it right now because I haven't switched to my terminal, but essentially what I'm doing is rerunning the same profile. So I'm just pulling it up here. I'll just switch back. Okay, so this command right here, asprof-e wall-i unsafe park, outputting into Mount Cassandra artifacts. I should probably have used a different name here. That's why I'm going to put a alias around it. Okay. So I will eventually figure out how to have a faster way to switch between these windows because it is annoying. Okay, cool. So this is exactly what I wanted to see. So this is sep worker wall clock time for these requests, which I think it's really, really important whenever you're going to do a performance profile. Let me talk for a minute about why I'm doing this. There's a few things that you can be measuring. You can be measuring CPU time, but CPU time is technically not like when you say that you want to measure CPU time, if a thread submits an IO request, you're not going to see the time that the IO took when you run one of these profiles. And the reason for that is because it's considered off CPU time. So what's really helpful is to have a couple different ways of measuring. One is when you look at CPU time, you might see that you're spending time in LZ4 decompress, but you may not see that you spent the time doing this read off disk. So this is P read up here. So you might not see this. So the reason why you want to get wall clock time is if you want to get a more holistic understanding of your application, but you have to be really careful because any time that a thread is spent sleeping will also show up in this flame graph. So that's why I'll just, I'll just share this. This will work with EasyCast Lab. So if you're not using it, you'll have to tailor it to your environment. But the original command, here. So I'm just sharing that. So in case anyone's interested in kind of doing this, it's the ASProf. So and then I'll just put it right there. Boom, that's what you need. The other thing to keep in mind is that if you're interested in doing these tests and you're interested in kind of learning about new versions of Cassandra, EasyCast Lab does make it really easy. So this tool is not only what I use for my stream, but I'm also using it for my training. In fact, we had our first training session on Monday. It's already 2 days ago, and it was awesome. Like everyone, SSH is in. Everybody's able to kind of test things. It's very hands-on. It's designed to be a sandbox environment that you can break. And what's cool, the other thing that's cool about it is you get a whole bunch of versions out of the box, so you don't even really need to make any choices. You actually just have to rebuild the Cassandra image every now and then, and you'll get the latest 5.0 branch, the latest trunk, whatever. It automatically selects the newest version of the image. So it's really easy. So this is what I've used to figure out several critical, I would say several like major things that like can make a really big difference in performance. If you're using Cassandra 4.1, I recently worked with a couple of folks to fix this. I'm just going to show you because this is pretty cool. So I did one of these actually. This error, this issue I found as a result of this stream. And let's see. It's this one, Cassandra 19477. Do not go to disk to get hint store get file size. So here's what happened, and this is why this is such a scary bug. If you have a node that goes down, the other nodes start hinting. That's fine. That's great. That's what we want. But there is in 4.1 there was a check added for the size of the hint files. So if you start hinting, every time it writes a hint, it's checking the size of this hint file. So it's actually doing two things. One, it's trying to it's getting the name of a hint file, which doesn't need to construct it on the fly. That's taking up like, let's see, 10% of CPU time was spent generating a name that we ended up just fixing it. Like we don't need to generate it on the fly every time. Static name. And it turns out like the overhead of doing string.format is significant. Under the hood, it uses the regular expression engine. So it's like you're basically doing a regular expression across 3 items with a search and replace every time you write a hint, or all you want to do is get the name of a file. It's kind of ridiculous. Like, so that was an easy fix. That was a very, very straightforward fix. But the thing that made it additionally problematic is that we also spent time, and I'm just going to I'll drop this in the chat. We also spend a significant amount of time checking the file sizes on disk. So the size of the hint files, because you can put a hint file, like you can put a limit to the hint size. But the problem is going to disk for system calls, going to the system to get the file size is an expensive operation. And if you're basically constantly hitting the file system, it adds up to the point where if you look at this CPU usage, this is a so this graph is crazy. This is the before and after. The difference here, some of these points over here, like this middle area, it's not so much, but here it's significant. We're talking about under 50% CPU usage, jumping up above 40%. So a difference of 40% in CPU is a big deal, right? But it's not only that it's a big deal because of these metrics, it's a big deal about when it happens. So if you if you think back, like what I was talking about was hints. When do hints get written? When a node goes down. So if a node goes down in your cluster, all the other nodes are going to start to have additional CPU usage because they're going to be writing hints. They're going to be checking file sizes. They're going to be doing that regular expression thing I talked about. If you have a cluster with 2 DCs and the connection between the data centers gets interrupted, all the nodes will start hinting. All the nodes will have increased CPU usage. If you're pushing those nodes hard, like if you run your nodes at like 50 to 80% CPU, you might actually have additional node failures or timeouts or other issues because of the CPU usage being so high. This will later then trigger longer GC pauses, which increases CPU usage. This is such a major. So we're gonna hopefully have another release out the door that fixes this soon. But if you're running 4.0 and you have an issue with your cluster where nodes go down, sorry, not 4.0, 4.1. If you're running issues where a node goes down and then you like see increased CPU usage, it's probably this. There's actually almost a certain, it's almost certainly this, unless you disabled, unless you're running a custom patch or something. But this is a pretty serious problem. So if you're running 4.1, you are 100% going to want to get the latest update, because this has our fixing here, and the difference is you know, as you can see, is enormous. There wasn't just like, even if we look at like a low, this is what happens when it's like not doing much. So, you know, you might notice 5% on a system that's not very busy. But if you're pushing your cluster harder, you will see it. The harder you're pushing your cluster, the more writes you do, the more write heavy you are on your cluster, the more susceptible you are to this problem. The other problem with this is that if you're already running your cluster pretty hot, like if you're running at 70, 80% CPU, just taking nodes down to apply this update can actually cause a problem. So this is super careful. So this is like very touchy. Like I would be really, really careful going through the upgrade process. You definitely want to get this patch in. This is probably one of the more significant performance issues that I have found, and you're going to want to get that in. Anyway, the whole point is that this was all found using this tooling. So this, if you want to figure stuff out, like this is how I figure it out. It's open source. Definitely check it out. All right, so it's been about an hour and 15. I'm going to wrap things up here. It doesn't look like there's any questions. So I am just going to wind this down. I'm going to get all this profile information over to Caleb so that he can figure out what's going on, if there's any issues, and potentially, hopefully, get some performance optimizations in. Yeah, thanks for joining. Really, I always enjoy my my time where I get to just break stuff and see what happens. We're definitely getting some nice improvements out of these sessions. I think it's exciting for me to be able to bring like Caleb on and have him talk about what's going on. So if this sort of thing is useful, please let me know. If it's not, also let me know. Like if this is totally dumb, let me know. I happen to enjoy it, so I'd continue it, but I'm open to doing other things as well if they're useful. So anyway, everyone have a great day, and I'm Rusty Razorblade on the ASF Slack chat. Definitely join us in the Cassandra or Cassandra Dev if you're interested in kind of getting involved in the development of Cassandra itself. And all right, I will see you around.